All right, the last two for the Unit 2 FRQs involve the same system. It's a cannon of mass MC and a marble of mass MM. For number 4, students launch marbles of identical mass MM horizontally from a toy cannon of varying mass MC, where MC is always greater than MM. The students can attach weights to the cannon to change MC. Each time a marble is launched, the cannon slides backwards before coming to rest. That is a Newton's third law, as well as a conservation of momentum issue. The coefficient of kinetic friction between the cannon and the ground is mu. For each launch, the students vary the mass of the cannon and launch a marble with the same speed, v, relative to the ground. The students record the distance x that the cannon slides backwards. So part A says, without manipulating equations, explain how the distance x that the cannon slides backwards changes, if at all, when marbles are launched from more massive cannons. So the answer then stems from conservation of momentum, which is going to be equal for the cannon and the marble. Now, the marbles all have the same mass and the marbles all have the same velocity, so this is going to be constant, which I just spelled with a K. I was going to just write a K. So what happens here? If the cannon gets more massive, then its speed decreases, okay? And delta x, we know, is equal to initial speed times t plus 1/2 at squared. Now, the acceleration is going to be constant, so a larger initial speed is going to get us a longer distance. So a more massive cannon will slide back less, okay? So you could have also said work is equal to FD, which is equal to delta K. Since it will be going slower, delta K will be less. And since the force is going to be the same, our distance is also going to be less. So 1 point for using conservation of momentum to indicate that a larger cannon mass means a lower speed, or using a combination of Newton's third and second law. And 1 point for explaining why a lower speed means less distance. So 2 points for the qualitative part there in part A. Part B, they're going to give us an equation which may or may not be correct. Students find the following equation on the internet to describe the distance x that the cannon slides backwards. And so we have x is equal to the mass of the marble times v squared over 2 g mu over the mass of the cannon squared. Okay, so hopefully this is getting comfortable, or you've seen it before. Whether or not this is correct, is it consistent with our statement in part A? And the answer is yes. We said that x would be lower with a heavier cannon. So what happens to this formula? If the mass of the cannon increases, then the denominator increases and the entire fraction decreases. So this does say with increasing mass of the cannon, we get a decreasing x. Okay, so 1 point again for functional dependence. So by saying that x and the mass of the cannon are inversely proportional, okay, you get a point for that. And then 1 point for saying that, well, since the mass of the cannon increases, the distance it goes back decreases. So 2 points for part C. Excuse me, that was part B. I was getting ahead of myself. Part C, if constant horizontal forces were exerted over the same distance on the cannon and the marble after the launch, which object would require a force with a greater magnitude to completely stop it? Without manipulating or referencing equations, explain your reasoning. So, more force will be needed to stop the marble because the marble has more kinetic energy. So more work needs to be done. So I'm going to write some formulas even though they said not to. I'm going to explain why that is. Okay, we have mv, or I should say m delta v equals m delta v for the cannon and for the marble, right? Now we know that the cannon has a larger mass and therefore a smaller velocity. The marble has a smaller mass and a larger velocity. So even though their momenta are equal, right, their kinetic energies are not. Okay, and kinetic energy favors the velocity. So even though the cannon has a larger mass, it's going to have less K. And we've done this before, but it's time to remember that. And the marble is going to have more K because it's going faster, and we square that. So you can, since they definitely said don't use formulas, just say even though they both have equal momenta, the less massive object will have a greater kinetic energy. Okay, then you can say you got to do more work to slow that kinetic energy down. And since work includes applying a force, that means we'd have to apply a bigger force. So, because the distance is the same. Okay, 1 point for saying 1 point for saying marble and attempt to justify it, and 1 point for using the work kinetic energy theorem for that. Part D, students correctly describe the following equation for relating the force exerted on an object initially at rest over distance d, the mass m of the object, and the final p of the momentum. So they get F equals p squared over 2 md. Again, is this equation consistent with your description in part C? So we said in part C, we'd need more force for the marble if everything else was held constant. So what we have here is that F is inversely proportional to M. Okay, so if the mass goes down, that means the force goes up. So the answer is yes. So 1 point for a claim consistent with part C, and 1 point for saying even though the momenta are equal, right, the mass of the marble is less. Okay, so 2 points for part D. All right, E, F, G, and H are the students' claims. Student 1 claims the mechanical energy of the marble is constant. I'm sorry, let me read the instructions. Students then discuss the mechanical energy of the marble after it's been launched by the cannon, but before it reaches the ground. Both students agree that air resistance is negligible. Student 1 says the mechanical energy of the marble is constant. There are no external forces exerted on the marble, so its energy does not change. Student 2 says the mechanical energy decreases as the marble falls. That happens because the gravitational force is doing work on the marble. So for student 1, neither is correct. Okay, the mechanical energy of the marble is not constant. It's going to increase. The speed of the marble is going to increase as gravity pulls it to the ground. There are no external forces acting on the marble, so its energy does not change. Well, gravity is an external force. So student 1 is wrong on both counts. So part E, neither is correct. Part F, both are wrong. Okay, so E is neither. F is both. 1 point for each of those. Right? Let's go on to student 2. The mechanical energy decreases as the marble falls. This happens because the gravitational force is doing work on the marble. Well, gravity is doing work on the marble, but that's increasing its mechanical energy. So the second statement is correct. The first statement is wrong. So again, 1 point for E, F, G, and H. And now we're going to move on to I. This graph shows the horizontal component of the velocity of the marble, that's the dashed line, and the cannon relative to the ground. Before time t1, the marble cannon system is at rest. At time t1, the marble begins accelerating within the cannon, and at time t2, the marble leaves the cannon. So if you take a look at that for a second, that should make sense. Most of the acceleration happens, well, all of the acceleration for the marble happens during t1 and t2, and the acceleration for the cannon is greater as well. If you look at the velocity of the cannon, it actually slows down because of friction after the launch. We've decided that air resistance is negligible, so the marble is not slowing down. So we're going to describe the motion of the center of mass of the marble cannon system during the time interval t1 to t2. So the answer is the center of mass moves to the right. The center of mass moves to the right during the collision. The only external force is gravity, is friction. And friction is acting to the right during the collision. There's no friction on the marble inside the cannon, so you don't have to deal with that. So the center of mass moves to the right during that collision. The only external force is friction, and friction is acting to the right because the cannon is moving to the left. So 1 point for the answer to the right. 1 point for indicating that friction is the external force, and 1 point for realizing that in order to move the center of mass of a system, you need to apply an external force on the system, and friction is the external force that's acting on that. So 3 points for part I.